Now, when Giles invited me to give this talk, I looked back and I had to think about this, and I realised that it is 18 years since I first put this slide up to talk about carbon dioxide in the atmosphere. I said in my lectures back in 1995 that by 2000 we were likely to hit 380 parts per million, which at that time was considered to be the tipping point for runaway climate change. This summer, the summer just gone, at Moa Luna, which is the observatory in Hawaii where they measure atmospheric carbon dioxide now, the atmospheric carbon dioxide concentration exceeded 400 parts per million on several days. If you look at the Earth from space, in the infrared spectrum, this is what it looks like. The average surface temperature is 287 degrees Kelvin, that's 14 degrees Celsius. It ranges from about minus 70 down in the Antarctic up to about plus 50 in Death Valley. But the average is around about 14 degrees Celsius, 287 Kelvin. What we have here are two sets of curves. The top curves are transmission spectra through the atmosphere, and the bottom curves are the absorption spectra of the chemical constituents of the atmosphere. I haven't included carbon dioxide at the moment. The way the planet stays in thermal equilibrium, bearing in mind that it's absorbing all this energy from the sun through this window in the absorption spectrum of the atmosphere, is by re-radiating a proportion of that energy, all of that energy to space, but it does it at a different wavelength. The planet absorbs all wavelengths, including visible light, including ultraviolet. That warms the structure, it warms the mass of the planet, but it doesn't warm it very much. And the planet then re-radiates as much energy to space as it absorbs, but it does it at a longer wavelength, therefore at a lower temperature. This curve here, 252 Kelvin, is minus 21 Celsius, which is the temperature the planet would stabilize at without carbon dioxide. You can see that that curve fits very nicely with this transmission spectrum, which is basically the inverse of the absorption spectrum down here. This is a window in the chemical constituents of the atmosphere which allows heat to escape back to space, but it can only do so at a particular temperature because all other radiation spectra are blocked basically by water vapor. When we add in carbon dioxide, which are these pink bars, you can see that that closes down this portion of the re-emission window. And by doing so, it shifts the concentration of radiant energy up the power spectrum. It becomes shorter wavelength, and you end up with a distribution which is centered closer to a curve at 287 Kelvin, which is the average surface temperature of the planet. It's this process, it's this limitation in the ability of the planet to re-emit the energy that is absorbed from the sun to certain specific wavelengths that creates the temperature at the surface of the planet. As we close this window down more and more, this spectrum is going to shift further and further to the left, meaning that as a result the planet must get hotter in order to be able to radiate heat at the correct spectrum to discharge the energy it's absorbed from the sun. So this process is inevitable as long as we continue to create a more opaque atmosphere in the region of carbon dioxide absorption. Well, I've got a bottle of water. Okay, I've got a bottle of water, I've got some black ink, and I've got a torch. So this is my atmosphere, this is my infrared radiation, and this is my carbon dioxide. So we start with an atmosphere which is optically clear in the infrared. Now, I've done a bit of maths, and I've calculated that in a bottle this size, 280 parts per million is 4 drops of ink. 400 parts per million is 6 drops of ink. Not very much. So let's have a look and see if we can tell the difference between 1, 2, 3, 4 drops of ink. Right, so that represents 280 parts per million, the historical average carbon dioxide concentration in the atmosphere. Shake it up a bit. Okay, and it's turned black. At 280 parts per million, you can no longer see through that. I can shine a light through it, and hopefully you can still see that there is transmission at 280 parts per million. That atmosphere still has some transparency. What do you think is going to happen if I add just 2 more drops to that? We better find out. So, 1, 2. 280 parts per million to 400 parts per million. It's not much, is it? 2 drops out of 6. Honestly, my torch is turned on. Okay? That's the difference that we're making at the absorption spectrum that controls the temperature of the planet. We are opacifying the atmosphere. And it doesn't take very much to make a substantial difference when you're talking about something which is kilometres thick.